let's have a look at back titrations today. So back titrations can be pretty hard, but we're going to make it simple by doing three things. We're going to go through the motivation on why we would do a back titration. We're going to go through some analogies to help us understand, and then we're going to go through some example problems. So let's start with the motivation for a back titration. Why would we even want to do a back titration? It's so complicated, right? So a back titration involves a couple of steps, but let's try to understand why we would want to even do it in the first place. So let's say that we have calcium carbonate. Calcium carbonate is just marble or chalk, right? So calcium carbonate, let's say you want to react with HCl, right? Because you want to figure out how much calcium carbonate there is in, say, a piece of chalk, right? Now the problem is that this is fine. This makes calcium chloride and water and CO2. Nothing interesting so far, right? The problem arises now. When you do a titration, you need to know when to stop. You need to know the end point of the titration, right? But the problem is this is going to be really hard to do for this one. Let me explain to you why. Let's say that I have something like sodium hydroxide plus HCl gives you sodium chloride plus water. For this reaction, I can use an indicator. I can use the bromothermal blue indicator, right? I can use the bromothermal blue indicator. I would add in, say, my sodium hydroxide into the beaker, into the conical flask. I would drip in my HCl, and then my bromothermal blue will turn green when I've reached the indicators. That's great. The problem is calcium carbonate is a solid, so it doesn't dissolve. You've probably never seen a marble bench dissolve when you add water to it. So that means that when you can't really add in any indicator to this calcium carbonate to show how it used to be basic, and now it goes towards a neutral endpoint. So that's the main reason why we can't actually do a normal titration for these things, because we don't have a good way to measure when the endpoint occurs. We have no idea where it is. I mean, we could do something like, if you add in like the HCl and you just watch for all of this to disappear, that's quite inaccurate. Titrations are meant to be really, really high accuracy, so that wouldn't be enough for us. And so this is where the back titration occurs. This is where the brilliance behind the back titration occurs, right? So the problem with the traditional titration is that the problem with using a normal titration for solids and gases is that it's hard to know when the endpoint occurs, right? And this is where the back titration brilliance comes in, right? So the back titration says, okay, look, I don't know where the endpoint is. I don't know, right? I'm just going to completely shoot past the endpoint and then work backwards, right? So I don't know how much HCl I need to finish this reaction. I'm just going to add a buttload, way too much HCl, and then we're going to work backwards to figure out how much there was here. Now, I think that this is easiest to understand using an analogy, okay? So let's say that you are at a car factory, right? And one day, some weird aliens come along and they deliver you, nice aliens, and they deliver you a big black box, right? Big black box. You can't open it, you can't drill into it, it's made of super hard stuff, you can't drill into it, alien technology, can't open it, right? It's a gift, and when you press a big red button on the front, what will happen is that it will spit out a car frame. Woohoo! Right? It'll spit out a car frame, right? Wheels not attached. And so you think to yourself, well, okay, cool, it spits out car frames. I don't know how many cars are inside though, right? I don't know how many car frames this alien gave us. It can't be that many, because it's a pretty big box, but it's not colossal. You estimate that there's probably less than 1,000 car frames inside. But you're still not sure. Is it 100? Is it 200? Is it 800? Is it 300? No one knows, right? So you come up with a sneaky plan, right? You say, okay, all right, guys, I'm going to give us 4,000 tires. I'm going to give us 4,000 tires. And what we're going to do is we're going to put on these tires on the cars, right? So everyone goes to work, pressing the button, putting the tires on, pressing the button, putting the tires on, right? So we have 4,000 tires initially, right? 4,000 tires initially. 4,000 tires initially. And then, after you come back, after a few hours of work, we find that there's only 1,200 tires left. So, how many tires were used in the construction process? Well, we must have used 2,800 tires used to build cars. So you can see that just from looking at the number of tires left and how many tires we had initially, we can deduce the number of tires that we used to build the cars. So we used 2,800 tires to build cars. Well, now you can figure out how many car frames there were. Because we know that, okay, one car frame needs 4 tires. Can't build a car with 3 tires, right? So now we can just do a little bit of calculation. You say, okay, I have 1 car frame, 4 tires. 2 car frames, 8 tires. 3 car frames, 12 tires, so on and so forth, right? So that means that if I wanted to use 2,800 tires, I will simply divide 2,800 by 4. I'll get 700 car frames, right? So basically tells me that there must have been 700 car frames. 700 car frames from that alien box. Right, so let's review that again. So we know that there was 4,000 tires. We were given 4,000 tires. And to figure out how many car frames there were, we saw that there's only 1,200 left when we come back after all the work. So we can therefore deduce that 2,800 were actually used to build the cars. And therefore, because one car frame requires 4 tires, to use 2,800 tires, you must have 700 car frames. Okay. Now, obviously, this is not chemistry, but we can use this as an analogy to understand roughly how our titration works. So to give you a better example, let's say that we come back to that calcium carbonate reaction. So let's say that I have this reaction once more, okay? And I'm going to now want to figure out how many moles of calcium carbonate there are. So remember, the problem is that we don't know when the endpoint of calcium carbonate is because we can't see the endpoint, right? So instead of just trying to drip the HCl in such that we just get the endpoint, we're going to completely fly past it and add in like so much HCl that it will completely just obliterate it, okay? So let's say that we have, some unknown amount of calcium carbonate. But to make this a bit easier, we're actually going to know how much there is. It's unknown, but just between you and me, right? Let's say it's 1 mole, right? But we're not meant to know that, right? Let's say that we add in way too much HCl, we add in 5 moles of HCl, right? So what's going to happen here, right? So the 1 mole of calcium carbonate, requires 2 moles of HCl. Well, and so what does that mean? That means that if I had 5 moles of HCl initially, and I'm going to consume 2 moles of the HCl, so therefore 3 moles of HCl left over. Now, sadly, I can't just look at it and see how many moles of HCl there are. I'm going to need another titration. Now this is actually pretty easy. We can easily figure out how many moles of HCl there are left, which just means a normal titration like this, right? Which you should be comfortable with. So we can just do this titration, and then, if there's 3 moles here, then we'll need to use 3 moles of the sodium hydroxide to reach the endpoint. And therefore we can figure out how much there was. Now, that is how back titration works. Let me run through it again, but this time we're actually not going to know how many moles of calcium carbonate there are. So I have a number in my mind, but you're not going to know it, okay? So, okay, starting from the beginning, there is an unknown amount of calcium carbonate. I know the answer, you don't. We add in 5 moles of HCl once more, okay? Now, now there will be some mole amount of HCl left now, right? How much is there? Well, I'll tell you. I had to use 4 moles of sodium hydroxide to neutralize all the hydrochloric acid that was left. So how much hydrochloric acid must there have been? Well, there must have been 4 moles. So if there was 4 moles of HCl left over, so the moles of HCl left is equal to 4, and the moles of HCl initially is equal to 5 moles. How many moles did we use, right? So we can think about, moles initial is equal to moles left plus moles used, right? That makes sense. If I had 5 cakes and there are 2 cakes left, then 3 must have been eaten, right? 5 is equal to 4 plus the moles used. Therefore, we used 1 mole, right? So that means that in this process of reacting, I used up 1 mole of HCl. There's 1 mole of HCl actually used. By molar ratio, I must have had 0.5 moles of calcium carbonate. And that's all that there is to back titration. To help you understand it more, we're going to go through some practice questions. Let's get right into those. So in this question, we want to determine the amount of barium carbonate in a seashell that's dissolved in some HCl. Then this HCl is reacted with sodium hydroxide to reach the endpoint. What is the percentage by mass? Okay. So what we want to have a think about here is that. So let's have a think about this. So the first thing that we want to do is we want to figure out the moles. We want to write an equation actually. The 2 equations that we're going to be using. Then we're going to have. So the first thing that we're going to do is we're going to determine the moles of sodium hydroxide that were actually used. We don't need that. CV 0.15 times 0.0125, which will give us. Okay. Let's have a think about this, right? So the number of moles of sodium hydroxide that we actually used, that must be the same number of moles as the moles of HCl left over, right? Because it's the moles of the HCl left over that will be reacting with our sodium hydroxide. Okay. Okay. Now let's figure out the moles of HCl initially. So we were told that there was 420 milliliters of 0.2. So initially we put in 0.084 moles of HCl. There's this number of moles left over. So we know that the moles of HCl initially, or total, right, must be the moles of HCl that we use plus the moles of HCl that are left. So we know that we initially have 0.084 moles. We don't know how many moles were used. Plus HCl 0.00187, 0.001875. So the moles of HCl used would be 0.8213 moles. This is how many moles of HCl that we used. So this number of moles we can go ahead and put underneath this one. That's how many moles of HCl that we used. I forgot to balance this equation. So therefore, the number of moles of barium carbonate, if we think about the molar ratio, should just be half of this number. It should be 0.041. Right, so therefore, the moles of the barium carbonate is equal to 0.041, 1 to 2 molar ratio, right? So therefore, let's figure out the mass of this, right? So therefore, mass of the barium carbonate is equal to the moles times the molar mass, which is the 0.041 times molar mass, which gives us 8.1 grams. Fantastic. Now, this was from a 59.1 gram sample. So therefore, percentage is equal to 8.1 over 59.1. Gives us 13.7%. Nice work. Let's try one more. Let's have a look at this question. So this one's a bit overwhelming. I would definitely encourage you to actually try it yourself. It looks really hard. It's actually much easier than it looks. So sodium chlorate found in household is the active ingredient in household bleach. Produces chlorine upon addition to acidified HCl, as shown in this equation. That's the chlorine. A 15 milliliter sample of household bleach is diluted to 100 milliliters. 25 mils of this solution is then pipeetted into a conical flask containing dilute hydrochloric acid. Excess potassium iodide is then added, which will react with the chlorine. So that's the chlorine that we generated in step 1, and that's the iodine that we're added with the potassium iodide. The potassium doesn't do anything. It's just a spectator ion. It literally does nothing. It could even be sodium iodide, because the sodium, potassium, they just don't do anything. The resultant solution is then titrated against 0.15 molar sodium thiosulfate solution and required this many mils of that. The sodium thiosulfate, so this thiosulfate reacts with the excess iodine there. Okay, so look, it's very complicated. In fact, this is actually a double back titration. So there's you back titrate. So it's a bit complicated, but I promise you it's definitely still possible. Okay, so let's have a go at part A, which is to calculate the amount of iodine produced in this solution, which again, if you actually try, it's actually not that bad. So we want to find the amount of iodine, right? So this is our iodine, okay? And we say that we need this amount of sodium thiosulfate to react with our iodine. Okay, that's not too bad. We say moles of thiosulfate, S2, SO3 minus 2 is equal to Cv is equal to 0.15 times 0.0172 is equal to 0.00258 moles. Okay, having a look at this molar ratio, right? If I had to use 0.0258 moles of this, how many moles of iodine must there have been? Well, it's in molar ratio, so therefore moles of I2 is equal to 0.00129 moles. So you just divide this previous number by 2 because there's a 1 to 2 ratio there, right? It's like if I had to use 100 wheels, 100 wheels to make cars, how many frames must there have been? There must have been 25 frames. Calculate the amount of sodium chlorate present in 15 mils of the sample. Sodium chlorate present in 15 mils of the sample. Okay. Now, we need a bit of trickery here, okay? So we can see that there is 0.019 moles of the iodine here. Now, we were told that an excess amount of potassium iodide is added. Right, an excess amount of potassium iodide is added to react with the chlorine. So if there was 0.00129 moles here, these moles must have come from here, right? 0.00129, which by molar ratio must mean there must be 0.00129 moles here as well. And this meant this number of moles must have come from here, 0.00129, right? And so that means if we want to figure out the amount of sodium chlorate in the 15 mils, well then we can see here that if we had this number of moles of our chlorine, then by molar ratio, they must have all come from here. I have 0.00129 moles of my chlorate. So therefore, there are 0.00129 moles of chlorate. Now, we need to be careful here, right? Because there's all this dilution garbage. A 50 milliliter sample of household bleach is diluted to 100 milliliters. 25 mils of this solution is then pipetted. So only 25 mils of the 100 mils was then pipetted to react with this dilute HCl that we have going on here. Okay. So to help you visualize this, right, let's imagine that I had a little 15 milliliter sample, right? A little 15 milliliter sample. Now, this sample is diluted. Now, does diluting, does diluting something change the number of moles in it? No, right? So I'm gonna dilute it from 15 mils to 100 mils, right? We can see that the number of moles has not changed. Okay, now, out of this 100 mils, maybe that should be a bit longer to keep it to scale. Out of this 100 mils, 25 mils is going to be pipetted out to be used with, right? So this blue section here is the part that's actually undergoing this reaction, right? Now, if you ever think about this, right? If I grab this diagram and I shrink it back to the size of my original one, it's roughly the same, so yeah. We can see that basically, right, the key insight that I want to give you is that this 25 mils of the 100 milliliter solution, that's a quarter of the solution, right? Therefore, we're only using 1/4 of the original number of moles, right? So what basically I'm saying is that, look, we have this number of moles of the chlorate, but that's from just this quarter, right? There's another, 3/4 there. So therefore, moles total is going to be 0.00129 times 4. So the total moles of chlorate that we have is 0.00516 moles. That is the amount of sodium chloride present in the 15 mils, right? This is the 15 mils. The 15 mils was then stretched to 100 mils, but that doesn't actually change the number of moles. It doesn't do anything besides change the concentration. And then we've used a quarter of that 100 mils, which means we used a quarter of the 15 mils in terms of moles, really. And lastly, determine the concentration of sodium chlorate in grams per liter. Okay. So first of all, we need to figure out the molar mass. So we need to figure out the mass of sodium chlorate. And Hey Siri, what's the mole mass of sodium chloride?
The answer I found is 57.959 atomic mass unit.
Um, 74. Grams per mil, so those 15 mils, therefore concentration is equal to 0.384 grams in 15 mils, which gives us 0.026 grams per milliliter. Hope you guys enjoyed. See you guys.